who else other than Joe from Vespa has raised really the bar of vector search for the entire community. So in the next talk, he will be talking about a lot of learnings. I'm hoping that is definitely going to happen, and some pitfalls to avoid when you are going on the path of neural search. So let's welcome Joe from Vespa with a big round of applause.
Yeah, thank you very much for that introduction, Atita. Yeah, here I am. Thank you for coming to my talk. I'll talk about some neural search failure cases. And my name is Joe Bergum, and I work on the Vespa team in Yahoo. And for those that don't know Vespa, so Vespa is an open source platform. It's basically a search engine, which allows you to search and filtering and a lot of capabilities for ranking. We just crossed 10 million pulls on our Docker image. You can run it on your laptop or on-premise or using our cloud services. And I've been actually working on the Vespa team since 2007. So you can tell I'm gray, old. And I've been working on search for some time. In this talk, I'll briefly highlight some pitfalls or things that you should be aware of when you're considering vector search or neural search or semantic search. There are a lot of fuss around this. Briefly talk about pre-trained language models, because we need to have some understanding of them to understand how we actually obtain these vector representations. And then I'll give an overview of 3 different methods for using them for search. And then I'll talk about embedding models, off-the-shelf embedding models, and what to watch out for when you are doing embedding retrieval. So embedding retrieval is another word for vector search. Yeah, and I'm really glad the previous talk introduced CTO failure queries at K. So that's great. And also on the Lucene linguistic and tokenization. So you now know about some of these. So this is a safe space. I won't talk about RAG or generative large language models, meaning that they're generating text. So you don't have to worry about that. So pre-trained language models. So language models in themselves, they don't necessarily need to be large. They don't need to be GPT. They don't need to be generative models. And Google had this excellent paper in 2017 where they introduced attention is all you need. Right? After that, we have all these papers is all you need. But it's basically about representations. And this talk will talk a lot about representations. And the genius idea was that they came out with this idea that you could train these neural networks using something called masked word language objective. So you could take text from the internet, from books, and then you could mask a word in the text, and then you can ask the deep neural network to predict the text, right? And there's a massive amount of text in the world, so you can train this, and then you obtain a language model. And this pre-trained language model can be used for different downstream tasks. And we here are interested in classification, search, but there are also more to it. And this transfer learning is about the pre-training gives you the language model capabilities, which is unsupervised, which is brilliant, right? Because you don't have to attend to the training. You just give it data, you mask the words, and you have a lot of data. You know, that data is produced by itself. But task-specific training, we are into supervised learning, right? Now we have to provide examples. Here's a cat, here's a car, here's a relevant document, or here's an irrelevant document. We have these label examples. So pre-training, task-specific training. And what is actually a language model? Well, my mom, she's a little bit afraid of language models these days because she reads the news and they're going to kill her. And I'm saying, I have many language models. They're saved on my computer. And that she gets a little bit more relaxed then. Basically, a language model is a tokenizer and has a fixed vocabulary. So Lucian here talked about tokenization before. And there is a deep neural network architecture. And there are different sizes. So you have some text, you tokenize that text, and map that into a vocabulary. Then you run it through a deep neural network, lots of weights, lots of matrix multiplications, and then you get a lot of vectors out. We'll touch more on that. But I'll first talk about language tokenization. So happy path tokenization. The cat sits on the table looking at the cat, dog, or whatever. Runs through the tokenization, you get some tokens, and you get some token IDs. Okay, this is great. But the vocabulary is fixed. So before you actually train this model, you have to figure out what's the vocabulary going to be. So for English, BERT-based models are typically 30K unique tokens. So if you take ISBN identifier, which is a unique string, you end up with multiple tokens like this. And that can have some interesting consequences. For example, a lot of people think that vector search solves spelling mistakes, solves all the problem in the previous presentation, right? Because there was a lot of linguistic processing to get this thing to work, and we have multi-vector or multilingual vector embedding models today. They will solve it. Well, not quite, because this text string, Elasticsearch versus Vespa, goes into this token representation. And if you insert a few spelling mistakes, then you have a different token IDs. And this has some interesting properties. For example, if you index the WordNet is a linguistic database of English, and you spell it correctly, annoyance, and you tokenize that into one token, run it to the deep neural network, get a vector embedding model, then do a vector search, and it comes up with pretty good frustration, anger, rage. But if you misspell it, the embedding retrieval will return loyalty, consciousness, treasure, which is not really semantically similar, right? So spelling still matters, unfortunately. Same for multilingual models. You also have English models and you have multilingual models. So multilingual models, they know more words. So typically you have a vocabulary of 100,000 words. So they know more German here, shout, tisch, which the English tokenizer doesn't know. Another limitation is that since these tokenizers were built like when these language models came out, they don't know a lot of new words, like COVID-19 is represented as 3 tokens, GPT, it doesn't know that, 2023, it doesn't know that. So there are a lot of these things about the tokenization that eventually impacts the model. That was a quick detour into tokenization. So before I introduce the neural methods, I want to talk about searching over data, right? We are all search people, and we have a mindset about, how we're going to implement search. And we're going to go with Elasticsearch or something. We put an inverted index. So in this presentation, I will try to lift us a little bit higher up. And the whole thing is about, in order to do this without scoring all the documents in the corpus, you need to come up with something that can represent your queries or documents. And for Elasticsearch, Elastic also has vector search now, but I use it as an example, is that you take a document and you run all the linguistic processing, stemming, whatnot, and then you come up with a model of the document, right? A representation of the document, which is a very high dimensional vector. But very few of the actual vector dimensions have a non-zero value, okay? And the same thing for the query, and you can take this query representation and the document representation, and then you can come up with a scoring, okay? So it doesn't need to be vectors, dense vectors, sparse vectors. It's like, okay, how are you going to represent that? And then there's supervised versus unsupervised. So BM25, BM25 is a scoring mechanism which is largely unsupervised. It only has 2 parameters that you can kind of tune and optimize. But there are alternatives where you can actually learn the representations of queries and documents so that for a given query, the actual relevant documents are closer or have a higher similarity than the documents that are not relevant for that query, right? And the motivation, of course, for doing this representational approach is that we avoid taking all our documents. We could do this, and then for each of the documents, score them according to the query, sort them by some score, and then you have your set of ranked docs. Instead, we want to build an index, right? So that we can accelerate this process. So instead of taking all the documents through, scoring all of them, you will have, for Google, you will have billions of documents. It will take ages and years to get a reply, and that's how we accelerate. So this is the motivation for having this representational approach to search problems. And you can accelerate these searches by building index structures. So for sparse representation, where you have very high dimensional search, but you have few non-zero values, you can use algorithms like the weekend algorithm, max score, BM1, which basically tries to eliminate or not actually fully score all the documents in your collection, okay? But for dense representation, we can build vector indexes or algorithms for approximate nearest neighbor search. There are multiple of them. I will talk more about them. And then we could use those algorithms to accelerate the search, right? And of course, I talked about scoring all the documents versus building an index. Then you can also have multi-phase retrieval and ranking, where you have billions of documents. You can shard this, and then you can gradually increase the complexity of your ranking function while still maintaining cost, because we have to think about cost as well. And with that introduction, I'll talk about 3 neural methods for search. They all have in common that they need labeled examples to shine. Right? There could be somebody else that has trained them, and you are pulling them and using them in your domain or for your data, but they've gone through labeled examples. You cannot take a language model that's been trained or a masked language model task and expect that model to shine for search in any of these capabilities. So you have the pre-trained model, need examples, then you have a fine-tuned model, right? You don't necessarily need to fine-tune it yourself. You might be able to pull it out of Hugging Face, etc., but somebody has done something with the model. And the cross-encoder model is the most, it's basically the one that has the highest effectiveness. It's best, but it's also very slow or computational intensive. It's the most effective. It has a high complexity. You have to basically take the query and the document and input to the neural network and then you have a classification head, but you have to input both the query and the document at the same time into the model, and you get a score. So how many of you have heard about this type of method of neural search before? Just 50%? Okay. But the downside with this model is that you're not able to do a representational approach, right? Because you need to input both the query and the document at the same time into the model. Then we have the bi-encoder models, and the bi-encoder models are representational models. They try to learn representations of queries and documents, and then we can use a similarity function to compare them with each other. And then you can use different similarity metrics like cosine, Euclidean, things like that. But the main point is that it enables you to index documents offline. So you can take your corpus of documents, run them through this document encoder, obtain that representation, store that in something, and at query time, you can encode the query and do the similarity calculations. And one thing that people don't, or many don't realize, is that the output of a typical BERT model, is a transformer model, is a vector per input token. So somehow, for using a vector database like Quadrant or vector field in Elasticsearch, you need to come up with this function that takes these output vectors and compresses it into one. And this is where output pooling comes in. So we have to find a mechanism to obtain a single vector representation. And here there are multiple different strategies. I think the most common one is simply averaging. So all this information here, all the vectors that are coming out, they are contextualized vectors. So each of the vector representations that are coming out are depending on each of the words in the input. Then most of the embedding models will just average that, and you have one vector to represent this text and one vector to represent this text. Then there's more advanced models, which instead of learning this full compressed representation of queries and documents, actually learns vectors per term. Colbert is one of those models, really promising model, but it's not pooling these vectors into one. So instead of learning one vector representation of the query and one vector representation of the document, it's learning token-based vectors. But both are bi-encoder style models, because you can encode separately the query and the document, and at query time you basically compress everything into this similarity function. And the key observation is that you're learning representations of queries and documents using labeled examples, right? So if you train a model here, on the left side here, there's a data set from Google called natural questions. So these are questions that real users have queried on Google search page, and the results were found in the Wikipedia. And they have a training data with like queries, documents, these are relevant, and then you can pick what's irrelevant, it's up to you. Then you can say, oh, dense passive retrieval, it's much better than BM25 measured in NGCG, okay? So that's a representational model which has been trained on this data set. If you take that model, the dense model, and take another data set, which is MS Marco, which is from Bing web search, not Wikipedia articles, but small snippets from very similar in length, very similar queries. Actually, the dense representation of queries and documents learned in this domain does not generalize to this domain, okay? So that might be surprising, but you are basically learning representations of documents and queries, and it might not transfer to your domain. So when you're pulling an embedding model from Hugging Face, it might have been trained on data like this, and you are trying to apply it to this, right? Which it might fail on this. So it's important to keep this in mind. And to summarize these three different methods, they are all trade-offs, accuracy versus cost. And my point is that the model and the representation model is not better than the examples it was trained on, right? And it's also very hard, for example, for bi-encoder models that represent a full segment of text into one vector and the query into one vector, and then try to interpret why is this hit here. So when the CTO calls you and asks, why is this result in number 2, right? You can only hand wave and say, yeah, it's likely something in the training data, right? You cannot explain that score, right? There's no interpretability. And that's where Colbert and the models that are learning word vectors instead, you're able to actually interpret the score, because they are BM25-like models, because they're summing of the terms. So it's easier to explain to the CTO why actually this hit is there. So we covered neural search techniques. So how many of you have used OpenAI embedding services or embeddings? Not that many, but quite a few. Embedding models from Hugging Face or something. Okay, so a lot of you have experimented with, I will call them off-the-shelf text embedding models. So some you're able to pull the weights and then fine-tune them further for your domain and data, right? There are lots of sentence transformers and guides on how to do that. And there are multiple dimensions here when you want to evaluate a text embedding model. So one thing is the size of the model. like how many parameters is in the neural network, right? So how many of you are used to running GPUs in infrastructure for serving? So there's actually quite a few. Okay, so that's one thing, right? So some of the models that are big, you might have to, for query encoding, you have to bring GPUs into the picture in order to do inference. Then finally, this model produces a vector embedding, and the dimensionality, like OpenAI, they have 1,536 dimensions. That impacts storage, memory footprint, and search latency. Sequence length, we briefly touched on, and then quality, accuracy, language capabilities, and also licensing, and if you can use this model commercially. One great guide that I find is this MTEB, Massive Text Embedding Benchmark, which is a great guide because they both provide task accuracy on multiple different tasks, search, classification. So I think there are 56 different data sets. And you can compare them, and then you can take note of their model size here in gigabytes, and then the embedding dimensions. And because then that gives you kind of, some of these are also open source so that you can download and fine tune for your domain to give them more examples. But there are also rumors about benchmark hacks that some of the accuracy numbers doesn't really match real world cases and so on. There's a lot of interest in this because if you are top ranking on this leaderboard, you also get more traffic. So you should anyway adapt and test them to your domain. And I touched on GPU, and these neural networks, the transformer models, they have this very naughty scaling properties, is that they are scaling quadratic with the input length. So if you're inputting a short query, they are not that complex to do inference with. If you are inputting a long text, here 512, that's a lot more compute to obtain the vector representation, right? But this also opens possibilities for what I call asymmetric serving, so that you, for instance, could use GPU for batch-oriented document processing, and you can use CPU inferences for queries because they are typically shorter, which then kind of simplifies the architecture in deployments. And of course, if you go down the route of choosing 1,536 dimensions from OpenAI, for example, you can have a much higher cost in terms of memory, storage, and also for searching. And Casper here touched on the quantization and stuff like that. And it's obvious that this model has way too many dimensions over what it actually brings when you can use quantization into one bit instead, right? So it really has too many dimensions because it was really cool, you know, to have a high dimensional vector. But you won't get 4 times accuracy by that, right? Okay, so now it's quiz time. Now we go into like the vector search part of it, right? This is where the vector databases or the vector search functionality in Vespa Elasticsearch comes in. And brute force might be all you need. And what do I mean by brute force? Brute force is that you are basically taking your corpus of vectors, taking the query, and then you're comparing the distance and calculating these things for every single document, okay? And then you sort them by the similarity score and you get your top documents. If you look at the embedding models from OpenAI, so we have to have 1 million vectors. So how many of you are dealing with data sets that are larger than 1 million? Okay. And if you have 64 gigabytes of memory bandwidth, so between memory in your computer and the CPU, okay? So how many QPS can that node support? Just think about it before. Approximately 10, right? Because you have 64 gigabytes of, you have you have 6 gigs of vector data, and you need to move that 6 gigs of vector data into the CPU, okay? And the bandwidth, how much you can actually move is roughly 64 gigabytes is what you can get from a modern server today. If you have one machine. If you have all the machine, then you're using, and now I'm not talking about at all any instructions, any acceleration, just moving the data from memory into the CPU, okay? So this is why vector databases are here to stay. This is why vector search functionality is important. This is why approximate vector search is important, because if you're going to do this at any scale, it's going to be really expensive, okay, very quickly. But it might be that exact search is all you need for your use case, okay? But when we're introducing approximate search, we have a way to speed up this. Instead of taking all the vectors and comparing it, we can build an index. And that sounds familiar, right? That's what we do with Elasticsearch historically, Lucene, whatnot, right? You're building an index to accelerate the search. And here there are many different algorithms and implementations in vector databases, in search engines. And here I call it the jack of all trade-offs, because there are so many trade-offs related to approximate nearest neighbor search algorithms. It's the speed up that you get, like how fast is it compared to brute force? They can be really fast. Quality, what is the error that you introduced by doing an approximate search instead of an exact search? What about properties like real time, adding vectors, removing vectors, growing from 0 to billions? What does it mean? And what in terms of resource footprint, index build time, and so forth? There are so many trade-offs related to approximate search. You might have heard about ANN benchmarks. So have any of you like spent time on ANN benchmarks when you have been researching vector databases and so forth? Just a few. Now that's disappointing. And I will spend some time to explain this graph. Recall is unfortunately an overloaded term, because we talk about recall in search all the time, right? And it means your system is able to retrieve the relevant information, okay? But recall in the vector search, it really means overlap. So what you do when you want to quantify the impact of doing approximate search versus an exact search is that you run the exact search, take a note of the vectors or documents that are returned, and then you take the approximate algorithm, and then you run the same search, and then you compare the overlap, okay? Is that clear? So ANN benchmarks, they measure a recall down here on the x-axis. So 0.6 means that only 6 out of 10 on average of the return results were the same as the brute force, okay? And then you get QPS, right? And 10 raised to the power of 3, how much is that? 1 million? No. Yeah, okay. So it's in 10 raised to the power of 2, 100,000, 10,000, okay? You agree? And this is with a single thread, a single search thread, okay? One thread, and it's getting this amount of QPS, okay? Which is pretty good, right? So if you have an algorithm that is here, you can do 1,000 QPS. If you have 8 CPU cores, you can do 8 times that, so 8,000 QPS, right? So most of these algorithms are brilliantly fast, okay? But you sacrifice accuracy, okay? You're not getting the same vectors back that the exact search, okay? Is it okay that we're not returning the same result as the exact search? Depends on the use case. So if I build an application that is using a retina scanner, okay? So I'm taking a fingerprint of my eye, and then I match it, and then I like, okay, so do you want that search to be approximate? No, okay? You want that to be exact. And it's very important that to understand that ANN, introducing ANN also impacts the search quality metrics, okay? And now I'm talking about the search metrics, the metrics that we care about, NGCG, are we retrieving the relevant result or not? And this is an interesting paper from SIG-IR, lexical accelerated dense retrieval. This has a lot of data, so I'll guide you through it. Class B is a dense vector model, 768 dimensions, okay? The collection is MS Marco. It has 9 million passages. The NGCG score on the graded judgments of that model doing exact search, right, which is the perfect, right? It's 0.715, okay? So that's what you're getting from the model if you're doing an exact brute force vector search, Okay. Now your boss says, okay, I cannot afford that. You need to use a vector database or approximate nearest neighbor search, something. And we want it to be super fast, okay? So you have those constraints. Now, what you see here is that here they're comparing multiple different methods. IVF, which is a technique, for example, exposed in Postgres, other vector implementation scan, HNSW, Vespa also uses that, I think also Quadrant, VV8, and so forth. But by setting these constraints, you see that the NGCG drops significantly, right? Okay, so the error introduced by approximate search is actually having an impact on the CTO complaints at K, okay? And the funny thing is that a BM25 implementation on this data set is roughly 0.5, okay? So by introducing vector search model for this domain, you are even doing it worse than BM25, okay? That's how much the error is. And then you've gone through embedding, inferences, storage of these embeddings, but the accuracy that's degraded so much that you are basically left with BM25 accuracy, okay? So it does matter. We also, on a Vespa blog post, did a similar experiment. This was a multilingual model where we demonstrated multiple different retrieval strategies, changing these HNSW parameters. This is an algorithm for approximate nearest neighbor search. And then we could simply look at the impact on NGCG. And you can see that we could obtain the performance of the actual original model, but we had to look at the parameters to actually increase the quality of the building of this graph data structure. Okay, so I think it's important to know that this is important. And we talked about neural search and the neural search paradigm shift and so forth. This is data from MS Marco, the same type of data sets in domain usage. You see that in general, NGCG is very high for these models that are using neural models or language models. But if you use an approximate search algorithm that is bad, you are basically bringing in all the cost without the benefit because you're going to be down here anyway. Okay, so then you basically, the CTO will still complain, but now you also will complain about the cost of GPUs and infrastructure and other additional vendors and whatnot in addition, and you still haven't solved the search problem, okay? So there are issues that you should be aware of. So the summary of this talk is that tokenization and vocabulary matters, unfortunately. I wish I could say that we could not deal with all this stemming and lemmatization and whatnot, and we could be over with, but it still matters because you still need those exact search capabilities, right? You expect to be able to search for a phone number or some exact things, right? So you need a search engine that actually has the capability of both vector search and exact search. And it's all about representations, and your data might not match up with the data that the model's been trained on. And on embedding inference, sequence lengths matter, dimensionality matters, and embedding retrieval, be aware that approximate actually means approximate. The A in ANN stands for approximate, and it does introduce an error. Okay. And I'm still active on Twitter, so if you hated it, you can shout at me there, and you can catch me afterwards, and we have some time for questions, so I'm all yours. It's always fun to be in between you and beer and good times, huh? So I'm sorry I kept you so long.
Brilliant talk, and I guess we already have a question here.
Hi, I have a question about tokenization. In the previous talk, we saw tricks like stemming and synonyms and removing stop words for your specific domain. Is that also possible with neural search? Like, okay, I have my specific tokens and I want to have that in a model. Is that easy to do, or do you need to retrain the entire model, or just for the fine-tuning step?
Right. So the problem is that the masked language model step, that where you actually tune the weights of the neural network, require this fixed vocabulary. So you need to figure out the vocabulary before you start that training process, okay? You can still use that architecture without the masked language modeling and adopt your data, your domain, tokenization, what matters, and increase the vocabulary size and then adapt it to that. So multiple, like Amazon, I think we have a representative from eBay here. When they write about papers, they adapt to their corpus before they start the task-specific fine-tuning. So yeah, it's not a definitive shortcoming, but if you're like me, that works on like smaller models from Hugging Face, it's still an issue, yeah. So, but with enough training data, if you have a lot of label examples, then you can learn that these representation, even if they are split, is that you can learn that type of representation. That's a great question.
Hey, thanks for the talk. Do you have any thoughts on which between NDCG and recall is a better metric to evaluate quality of search results on?
Yeah, that's a great question. I think it depends on in what context of search you are in, okay? So in the previous talks here, we saw examples of search results displayed on a very small screen, right? Where precision really matters. If you are implementing search for a legal search case for where lawyers want to find relevant information across different databases or previous case studies and whatnot, recall is also highly important, right? So you to find all the relevant hits. So I don't think there are metrics that tries to balance this, like mean, average, precision, and so forth. But yeah, depends on the domain. But the point here is that if you introduce vector search, whatnot, there are, of course, gains to be made by this, multiple different, but still measuring it, it's still the same. I think we have a lot of data sets out there that you can measure the performance of your search, and that doesn't really change it if you're introducing vectors or introducing boosting or introducing any technique. You know, you can still measure, you know, how many are actually buying my products like food, whatnot, right? You still measure it, and looks good to me at 10. It's also a good metric.
Hi, yeah, thank you for the talk. One question, since you mentioned Colbert, I think one problem comes with it might be that the amount of memory you need to store all these small token representations might grow very high. And I was wondering if you have some suggestions what you can do to do this. Is it, for example, does it make sense to use quantization and only store the quantized representation? And does it still work, or?
That's it's almost like I gave you that question before, didn't I? So thank you. I'll pay you afterwards. Yeah, so that's the downside with Colbert. We have some exciting things around Colbert in the Vespa pipeline, which will largely address the footprint, the storage footprint. We are implementing the Colbert V2 paper in Vespa, so meaning that you don't have to pay the same storage footprint that you do. We do use a similar technique described by Casper here. Binarization. So instead of storing a very large vector, you're storing a more compact representation, and the accuracy degradation is less than 2%, even in out of domain data set. So that's just around the corner. That's why I'm selling it. So yeah, look out for that.
Okay, thank you.
Yeah. So was it 50 euros?
Hi, thank you for your talk. I have two questions. One is related to this slide because
This one?
Yeah, you blocked me on Twitter, so it might be a trap. And the second question is that how can you find a perfect threshold when you should stop doing vector search? So for a traditional search, when you find for a non-existent thing, you will get 0 results.
Yeah.
In vector search, you'll always find something, but it might be absolutely irrelevant.
Yeah.
But how to distinguish what is relevant, what is not?
Yeah. The first question I will address, I didn't realize. Number 2, it's a very tough problem. And the score depends on like how to, because that's a really important point. With nearest neighbor search, everything is a neighbor. Okay, So it's just the degree of distance. How are you gonna decide if this is not relevant or not, okay? I think that also require another step of training a model for that, because it's gonna be query dependent, how long the query is, and so forth. You cannot simply say cosine similarity is 0.7 below that. It's gonna be trash, okay? So yeah, I don't have a good solution.
Okay, thank you.
I think there was a similar discussion. I mean, it was a Bergum topic from me in MISIS, that how do we determine this K?
Yeah.
Because it is the elephant in the room, especially when we talk about vector search.
Yeah, and also when we talk about like Elasticsearch VB8 reciprocal rank fusion, is that you don't know when you're fusing this result, you don't really look at are these rubbish from the vector report. You just blend them into the main algo, right? So some cutoff there, yeah. But there's something that we are aware of. There are multiple ways to drop documents out of Vespa, like a rank score drop limit, cosine similarity, whatever. So there are a lot of options there, but we don't have the final solution in terms of a score threshold, because it also depends on the models that you're using. Yeah.
For sure. Any more questions? We're just in time, I know.
Great.
I didn't even have to give you a time warning. Appreciate that. So once again, give a big round of applause to Joe.
Thank you.
That was a great talk.